This video is going to show you how you can use the PWM protocol to be able to play a hopefully well-known tune through the peripheral buzzer. We'll discuss the Raspberry Pi Rainbow Hat and its actuators, in this case the Piezo Transducer, which is a buzzer that we can make play the Pokemon theme tune. Let's get started. PWM, or PWM, stands for Pulse Width Modularisation. PWM works with a single pin on your board and can be described as a digital square wave signal, where you can control the frequency of the wave and the duty cycle. This means you can send a signal down the pin, changing these properties, and your peripheral can react to these changes. Our Raspberry Pi is now plugged in and connected via ADB, ready for development. We have the Rainbow Hat connected to the top of our Raspberry Pi. This hat has a lot of peripherals, and amongst them the Piezo Buzzer. We're going to code our app so that the buzzer plays a little tune for us. You can't see the transducer, but it's under the top right hand corner of the LED screen. If you look at the back of the Rainbow Hat, you can see it's soldered on. When working with the Rainbow Hat, we can see how each of the peripherals on the hat is connected to our Raspberry Pi by looking at the pinout diagram. To understand how each peripheral works and determine the protocol needed to talk to it, we should consult the Rainbow Hat documentation and, if needed, the specific peripherals datasheet. In the documentation shown here, we can see the buzzer described as the Piezo Transducer, and it says it is connected to BCM13 or PWM1. This is the hint we need to tell us to use PWM protocol for our communication with the buzzer. Now let's double check the pin we need to use by referencing the Rainbow Hat pinout diagram. Looking at this diagram, we can see at the bottom left it shows BCM13 buzzer. Clicking on this, it then explains the alternative name is PWM1. We should remember this for later reference. Okay, let's program the buzzer. Here I have an Android Things project already set up in Android Studio. If you aren't sure how to get your project to this point, you can revisit the previous First App lesson for instructions. First, we create an instance of the Peripheral Manager service using this code. This is the Android Things SDK class that allows us to open connections to different board pins using the different available protocols. Using this instance, we want to open a PWM connection with the pin address we saw earlier on the pinout diagram. When we open this connection, we are given back a PWM bus variable that will now allow us to communicate using the Android Things SDK PWM class. We'll use this variable in multiple Android activity lifecycle methods. That's why we make it a field. Notice that we have to wrap the open PWM call in a try-catch block. This is because the method, and most other methods we will use in the future, all throw a potential IO exception. This is due to the fact that we are dealing with hardware, and at any moment the pin or the peripheral could become unavailable. At that point, calling the method would throw this exception. We are assuming that all our wires are nicely connected, and if we do get one of these IO exceptions, it would be really bad for our app, and actually, we want to crash straight away so that we can diagnose the problem as soon as it happens. That's why in the catch block, we throw an illegal state exception, as we are not expecting nor wanting this to happen. This is known as failing fast and is a clean code best practice. The benefit of this is that our bus variable is either a fully instantiated field at this point, or our app has crashed. Therefore, from this point on in the code, there is no need to check if our bus field is null. It never is. Opening a connection to a pin is capturing this pin as your resource, and like with all resource management, it is good practice to release resources once you have finished with them. Also, if we have an open connection to a pin, no other code can open a connection to that same pin until we close our connection. Since we open the connection to our pin in the onCreate method, we should use the symmetrically matching pair from the Android lifecycle to close the connection. Therefore, we close the PWM bus connection in onDestroy using this code. Again, close can throw an IO exception. We can't do anything about this if we get an exception, but we can log it out so that we know next time our app starts if something unexpected had happened in the past. The Piezo Buzzer works by us sending a repeating pulse at different frequencies to produce different sounds. Before we select these frequencies, we have to configure the duty cycle with this code. The duty cycle describes the width of the pulse inside of the frequency, and for a buzzer, this equates to the volume of the sound. The duty cycle API takes a percentage between 0 and 100. We select 50% as this equates to the buzzer being at its loudest. A quick note about music. Musical notes require two things, a pitch and a period. The pitch is the sound the note makes, and the period is for how long that sound is made. We are going to play the Pokemon theme tune on this buzzer. For those of you who don't read music, I have done you the courtesy of converting this music sheet into Java code. Each pitch becomes a frequency, and each period becomes a duration. There are more durations and frequencies in reading music, but I have just created the minimum we need to play our song. These then make up our note class, A frequency note has a duration and a frequency. A rest note has a duration but no frequency. The final music for the Pokemon theme tune looks like this. If you have the time and inclination, you can now convert any piece of music to this form. Now we have our buzzer's volume configured and our music ready to play, let's set up our music loop so that we can play some notes. Back in the main activity in our app-on-create method, we create a handler thread with this code. A handler thread is a thread that has a looper. Having a looper means that we can post messages or runnables to a queue, and the handler thread will receive these runnables and execute them one at a time. This is the same way the Android main thread works if you have ever used the runOnUI thread method. However, we are creating our own background thread to communicate on with our buzzer. To post runnables to the handler thread, we create a handler that requires the looper from our handler thread. It looks like this. Using this handler architecture allows us to communicate with our buzzer peripheral off of the main thread and so have full control of when we send notes. This is important for our note playing buzzer because we are going to post a runnable each time we want a note played and then pause the thread waiting for it to finish playing the note. This keeps a nice constant speed and will ensure a smooth playing and listening experience. Let's play a note on the buzzer. First, we create a runnable so that we can post it to the handler thread. Then we set the frequency the buzzer is going to play the note at. It is scientifically known that middle C equates to 261.63 Hz, so let's use that as an example. Now we enable the PWM signal to be sent with this code. We want the note to play for a certain duration for now, let's say 1 second. Use the system clock like this to sleep the thread for 1 second, which means the peripheral will carry on playing the note for that long, and then we disable the PWM signal again with this code, stopping the note. Hook up the runnable to play when the app starts, adding this code to the onStart method. Have the runnable repeat itself by posting again every time it gets to the end. And for best practice, always remember to remove callbacks using the Android lifecycle symmetrically matching method, which in this case is onStop, like this. Run the app and listen to that middle C note play. How repetitively annoying is that? Now you understand how to play a single note and make your threads wait until the note has played, let's hook up the Pokemon theme tune. As a reminder, here in the music class is the notes we want to play. We'll keep a queue in the main activity called Song, and this will hold the notes we want to play. Because it is a queue, we can poll for the notes in a first in, first out manner. Add the Pokemon music to our song in the onStart method with this code. We use the song queue to determine what notes we want to play next. Get the next note from the queue with this code. Now that we have the note, let's replace playing middle C with the frequency from the note. Also, the period is now determined by the note as well. The last thing we need to do is a special case with musical notation. Music has the concept of a rest note. It takes a beat, but doesn't play any sound. So if we need to play a rest beat, we should still pause our thread to wait for the beat, but we don't want to tell the buzzer to play anything. You can do it like this, with checking the note type with the isRest method. And the last thing to do is check if our song has finished. If it has, i.e. if the song is empty, we return from the runnable with this code. Let's run our app and check your Rainbow Hat to hear the buzzer playing the Pokemon theme tune. That's it! You now understand how the Android thinks PWM communication with peripherals works. You can interface with a piezo speaker, controlling its duty cycle and frequency, making it louder or quieter, and playing notes. This knowledge also transfers to other PWM peripherals, such as other types of speakers, servo motors, or LED dimmers.